Okay, we're going to start chapter 8 today just with basic matrix vocabulary and showing how matrices are related to systems of equations. So definition of matrix: if m and n are positive integers, an m by n matrix is a rectangular array with m rows and n columns. So for the first one, I'm just going to determine the order of the matrix. The order is the size of the matrix based on the rows and columns. So because A has 3 rows and 2 columns, I call this a 3 by 2 matrix, or its order is 3 by 2. If I look at example B, it's rows by columns. So there's 1 row and there are 4 columns. So it's a 1 by 4 matrix. For C, it has 2 rows, 2 columns. So it's a 2 by 2 matrix. And then for D, it has 1 row and 1 column, so this is considered a 1 by 1 matrix. Okay, so that's what, if they're asking for order, they're asking for the size and they want it to be rows by columns. Okay, one other note vocabulary-wise, if I want to name a specific member of the matrix, so for example, if I want to identify the 7 and I want to tell you exactly where it is, we use A for the term. And that's in row 3, column 2. Okay, so the number that is in row 3, column 2 is 7, and that's the way I would describe it. If I wanted to talk about, let's see, this one right here, I would say A, the element in row 2, column 1 is 1. That's just notation so that if you see that, you understand what they're saying. Okay, for number 2, it says write an augmented matrix for the system of linear equation. An augmented matrix normally represents some kind of equal sign. Okay, we use matrices often with computers. The problem with computers is they just want digits. They don't want to actually know. They don't want the variables at all. Okay, so an augmented matrix, it normally has a dashed line here. It could be a solid line here, but when I rewrite a system as an augmented matrix, I care only about the coefficients and the constants. So I'm going to make the first column x's, the next column y's, and the third column the constants. So since it's 3x plus 5y equals 11, I write it like this. For the next one, negative 1x, 2y equals 7. And these represent the exact same system, and we're assuming that this is the x column, this is the y column. The dashed line shows you what it equals to on each case. Okay, so for B, I'm going to represent this system again as an augmented matrix, and the augmented matrix is just used to represent some kind of equal sign. And sometimes they don't put the little dash line on the augmented matrix, but it's normally useful just so you can keep track of what equals to. Okay, so there are 3 variables, so I'm going to keep in mind, I'm going to do x, y, z for my 3 columns. So for the first equation, that's 1x, 1y, 1z equals 0. Okay, for the next equation, 3x plus 5z equals 0. So I have 3x, I have 0y, so I have to put a 0 there. 5z equals 4. And then for the last equation, negative 1x plus 2y, there's 0z, so I have to put a 0 there, and I put a 1. Okay, and again, this matrix represents this system, and this is the x column, the y column, the z column, this equals, and these are the constants. Okay, and these are interchangeable. Okay, so for number 3, we're just going to do it the opposite way. They are giving you the system, and it's augmented. They want you to rewrite it as a system of linear equations, so using x and y, or which other variables. So this is the x column, this is the y column. Okay, so for the first row, it's saying x plus 2y equals negative 7, 3x plus 5y equals 20. And I could solve it if it asked me to. Okay, so for B, it has 3 columns, so we're going to go with x, y, and z. So 3x minus y plus 5z equals 10. X, I don't have to write anything for y, plus 6z equals 0. And then for the last column, there's no x's, there's no y's, so z equals negative 4. Okay, the last thing we're going to do is just play with elementary row operations so we can make row equivalent matrices. Okay, so the first thing you can do in an elementary row operation is you can interchange two rows, and we do indicate this. Whatever move we do, we're going to indicate how we change the matrix. So if I interchange two rows, so say I change row 1 with row 2, I would write this to show that I switched row 1 and row 2. Okay, you can also multiply a row by a non-zero constant. So for example, if I wanted to multiply row 3 by 5, I would say 5 times R3, and that's allowed in an elementary row operation. We can also add a multiple of one row to another. So I might want to do 2 times R1 plus R3. That's another thing that's allowed in elementary row operations. Okay, so for this last example, we're going to perform the row operations, and then we're going to write the resulting row equivalent matrix. Okay, and then we're just going to play with this even though we have no idea why we're doing it. Okay, so if I look at A, I see the matrix I'm starting with. It's augmented, so I'm going to go ahead and keep the line there to remind me. You don't have to put the line, but it helps keep track. Now, according to the indicated directions, the only thing I'm changing is the third row, which means the first row stays the same. The second row stays the same. For the third row, I'm going to replace it with row 1 plus row 3. So I'm going to look at row 1 and row 3, and I'm going to add them in my head and write the result here. So in the first column, 1 minus 1 is 0. 2 plus 3 is 5. Negative 4 plus 5 is 1. 1 minus 4 is negative 3. And this is a row equivalent matrix because the only thing I changed was based on some kind of elementary row operation. Okay, for B, again, they tell me what I'm starting with. I'm starting with this matrix. The only thing they want me to change is the first row. So the other two rows are going to stay exactly the same. Okay, so for the first row, it's saying replace it with negative 1/2 of row 1. So I'm going to go back and look and see what row 1 looks like. Okay, and if I do negative half of negative 2, I get positive 1. Negative half of 6 is 3. Negative half of 0 is 0. Negative half of 8 is negative 4. The other two rows did not change, so I copy them the exact same way. Okay, and this is a row equivalent matrix. The only change I made was by using an elementary row operation. And eventually there will be a purpose to this, like next class, but for now we're just doing it randomly. Okay, for C, it's a smaller matrix, and it looks like I'm keeping the first row the same. Okay, so the first row, I keep it 1, 4, 0. Now for the second row, I'm going to replace it with 3 times R1 plus R2. So I'm kind of doing two things at the same time. So I'm going to go column by column. So in the first column, if I do 3 times 1, I get 3. And then if I add negative 3, 3 plus negative 3 is 0. And I'm just putting the results here. Okay, I'm going to go to the next one. 3 times row 1. So 3 times 4 is 12. 12 plus 2, 14. And then the last column, 3 times 0 is 0 plus 5, 5. Okay, and this is my row equivalent matrix because I did an elementary row operation. Okay, one last one. We're going to change 2 of the rows on this particular one. So for D, it looks like the first row stays the same. Okay, now the second row, I want to replace it with row 1 plus row 2. So let me look, row 1 plus row 2 are these two, and I'm doing this in my head. So if I go in the first column, 1 minus 1, 0. 2 plus 5, 7. Negative 3 plus 2, negative 1. 4 plus 0, 4. Okay, so my row 2 is complete because I added row 1 plus row 2 and I put the resultant. Okay, for the last one, row 3 I'm going to replace with twice R2 plus R3. And I am going to do this on my head. If you want to do it on the side to show your work, you could do it on your side. You don't need to show your work though. Okay, so twice R2 plus R3. So if I do twice of this, I get negative 2 plus 2, 0. Okay, twice this, so 10 plus 0. Twice row 2 is 4. 4 plus 1 is 5. Twice 0 is 0 plus 3 goes down to 3. So then that's my third row replaced. And again, this will eventually have a purpose to it. For now, we're doing it randomly to get you used to working with matrices.